So, hello everyone. I'm Gitanjali. I'm a PhD scholar from IIT Delhi. I welcome you to the 12th live section of the course Quantum Mechanics 1. And in this section, we will solve the problems that is related to Wigner-Eckert theorem and some of the application of Wigner-Eckert theorem. As well as besides this, we will also solve some of the problems that is related to delta function and as well as potential barrier, because I haven't solved this problem in my previous live section. So today I will solve the problems that is related to both Wigner-Eckert theorem as well as delta function and the potential barrier. So without further delay, let's get started. So this is the first problem. So let me read out the question. So it's one of the application of Wigner-Eckert theorem. So the question says, construct a spherical tensor of rank 1 out of two different vectors u, ux, uy, uz. So let me write the question. So there are two vectors. One is u equal to ux, uy, uz, and another one is v, which is vx, vy, and vz. Now the question is asking explicitly write T1. So let me read the question again. So the question says construct a spherical tensor of rank 1 out of two different vectors u, ux, uy, uz, and v, vx, vy, and vz. So using these two vectors, you have to construct a spherical tensor of rank 1 and write this tensors, which is T1 plus or minus 1, 0, in terms of ux, uxy and z, and vxy and z. So you have two vectors, and it is asking about construct a spherical tensor of rank 1. So what will be the expression for spherical tensor of rank 1? So you know that scalars are spherical tensor of rank 0 and vectors are spherical tensor of rank 1. So the question is asking about to construct a spherical tensor of rank 1, which is to construct a vector in terms of this spherical tensor component. So how can you construct a vector out of two vector which is given u and v? So we can take the cross product of these two vectors u and v, which is w equal to u cross v. So this cross product of these two vectors will give you a vectors of vector w, which is a spherical tensor of rank 1. So now let us calculate what is the expression of this cross product. So how you can calculate the cross product? So it is nothing but ijk ux, uy, uz, vx, vy, vz. Right? So now you can write it in terms of the components x, y, and z, which is x is uy, vz minus uz, vy, ik plus the ik would be uz, vx minus ux, vz, jk And the last one would be kk, which is ux dy minus uy vx. Now you can write this I cap component as wx, this j cap component as wy, and the third term is wz. Okay, so now you got the Cartesian representation of this vector w. Right? So now to represent it in terms of spherical tensor, what can you do? So you have to take, so it's a spherical tensor of rank 1, and when q is equal to 1, so I am representing in terms of k, t, k, q. So for t11, you can write it as a minus wx plus iwy whole divided by root 2. This is 1. The other spherical tensor, which is q minus 1, would be wx minus iwy divided by root 2. And the third one, which is t10, would be the z component. Right? So these are the representation for the spherical tensor of rank 1. So now the question is asking about to represent this tensor in terms of ux, uy, uz, and vx, vy, vz. It is asking about write it in terms of ux, uy, vz, and vx, vy, vz. So what you can do? You just put down the expression for wx, wy, and wz, which is for wx. If you see this equation, then wx is nothing but uy vz minus vz, sorry, vy uz. So this would be vx uy vz minus uz by, and wy is uz vx minus ux vz, and the last term is wz, which is ux vy minus uy vx. So you have to put this expression in equation 1, equation 2, and equation 3. So if you put it, you can easily get this t11 would be minus 1 by root 2. It would be uy vz minus uz vy plus I times uz vx minus I times ux vz. Similarly, t1 minus 1 would be 1 by root 2 uy vz minus uz vy minus I uz vx plus I ux vz. The third term would be t10, which is equal to wz. So it would be ux vy minus uy vx. So this is the final answer to the question. So the question was asking about the spherical tensor of rank 1. So for this, we have to find out a vector in terms of these two vectors u and v. So now the first part of this question is done. So let us move to the second part. So for the second part, so it is asking about construct a spherical tensor of rank 2 out of two different vectors u and v, and write down explicitly t2 plus or minus 2 plus or minus 1 0 in terms of ux, y, z and v, x, y and z. So it is asking me about construct a spherical tensor of rank 2. So for rank 2, so you know that the vector u and v are the spherical tensor of rank 1. So if you want to find out a spherical tensor of rank 2, what you can do, you have to take so let us first write down the expression for the vectors in terms of spherical tensor. So for u, you know that it is u plus or minus 1 is 1 by root 2. And there is a minus plus sign ux plus or minus iuy. u10 would be uz. And for v, you also have u1 plus or minus 1 is minus plus vx plus or minus I vy divided by root 2, and v10 would be vz. Okay, so now if you want to find out a spherical tensor of rank 2, let us see the first component, which is T2 plus or minus 2. So it is Q either plus 2 or minus 2. So you know that if Q is plus 2 or minus 2, then Q should have either plus 1 or minus 1, and V should have plus 1 or minus 1. Each has K equal to 1. So if you take U and V of plus or minus 1, then you will get T, which have Q plus or minus 2. So now let us put the expression for U and V, which we have written here, these two equations. So the final one would be, this is 1 by 2 ux plus or minus iuy and vx plus or minus ivy. So now you just have to multiply the individual term. So the first one you will get is us vx, and so there will be a term which is minus uy vy. So uy vi you will get by taking these two terms, right? There is a I here, I, so I square will be there. So I square will be minus 1. So you will get this term plus there is a I term which is plus, so it will be plus or minus I by 2 ux vy plus uy vx. So these two terms you will get by taking ux and ivy, and another one is iuy and vx. So this is the final expression for t2 plus or minus 2, which is half ux vx minus uy vy plus or minus I by 2 ux vy plus uy vx. So this is for t2 plus or minus 2. Now for t2 plus or minus 1. So here q is plus or minus 1. So plus or minus 1, you can get it either by taking u1 plus or minus 1 and v as 0, or you can get it from u0 and v plus or minus 1. So that will be normalization factor, which is root 2. So now you have to put the expressions for u1, the u1 plus or minus 1 and v1 0, v1 plus or minus 1 and u1 0. So if you put it, you will get the final expression would be half, there will be minus plus sign, ux plus or minus iuy vz plus uz, and there will be a term vx plus or minus I vy. And there will be a minus plus sign here also. Minus plus sign here also. So now you just have to simplify the expression. Okay. So let me pull out the minus plus sign. There will be a half here. And this is ux vz plus vx uz. And the other term are minus plus or minus I uy vz plus vy uz. Okay, so you just have to multiply vz in individual term and separate out the real terms and imaginary terms. Now the third part is, which is t2 0. So t2 0, you can get it only when u and v, both vectors f q is 0, right? Uh, q is either for u, no. So for 0, it would be for u, it may be 1, for v it is minus 1, so that 1 minus 1 would be 0. Or you can have v as minus 1 and u is plus 1. So in that case, it is also 0. Or you can have u is 0 and v is 0. For u, it is q is 0 and for v, q is 0. So in that case also, you will get 0. So what I mean is, you can have this choice where for u, it is q is plus 1, for v, it is minus 1. Or you can have for u, it is minus 1. And for v, it is plus 1. Or you can have u 0, v 0 divided by, there is a normalization factor which is root 6. So now you have to just put the expression for these individual terms. So for this term, you have to put the expression. So u1 plus 1 is nothing but minus ux plus iuy divided by root 2, and minus 1 is v1 minus 1 is vx minus ivy divided by root 2, plus there will be minus 1 here for v1 plus 1. So u1 minus 1 is ux minus I uy vx plus I vy divided by 2. The third term is 2 times uz vz whole divided by root 6. So now if you solve it, so I am writing the final expression. So you will get 2 uz vz minus ux vx minus uy vy divided by root 6. This is the answer you will get for t to 0. Okay, so now you have all the components, spherical tensor t to 0. This is t2 plus or minus 1 and t2 plus or minus 2. So this is how you can construct a spherical tensor of different rank using two vectors, two arbitrary vectors. So now let us move to the third question. Please go through the question once. So let me read out the question. So the first part is, so let us solve by part by part. So let us see the first part. So the first part is write xy, xz and x square minus y square as components of a spherical irreducible tensor of rank 2. So for a spherical tensor of rank 2, we have to write the components, matrix component xy, yz, xz and x square minus y square. So in the previous problem, we have already calculated the representation for spherical tensor of rank 2. So use this one t2 plus or minus 2, t2 plus or minus 1, t2 0 to find out the answer to the first part. So let me write down the expression for the spherical tensor, then we'll solve it. So for t2 plus or minus 2, the expression was half ux vx minus uy vy plus or minus I by 2 ux vy plus uy vx. So this is for t2 plus or minus 2. So now you have x, y and z components. So instead of ux, uy, uz, you have x, y and z, and instead of vx, vy, vz, you have x, y, z. So that means we have to put ux equal to vx equal to x, uy equal to vy equal to y, and uz equal to vz equal to z in this. So you have to put it in this expression. So the expression becomes when you put x for ux and vx and y for uy vy and z for uz vz. So it will be half. It will be x square minus y square plus or minus I by 2. So this will be 2 times xy. So the final expression would be half x square minus y square plus or minus I x1. So from this, so you got this for t2 plus or minus 2. So you are saying there are two terms here, which is one is x square minus y square and another one is x1. So you can represent these two terms in terms of spherical tensor. So for that, what you have to do? We have to do the algebraic manipulation. So you know that T2 plus 2 is half x square minus y square plus ixy, and T2 minus 2 is half x square minus y square minus ixy. So now if you add these two terms, what you will get? You will get x square minus y square, and these xy terms will cancel with each other. So that means x square minus y square is T2 plus 2 minus, plus T2 minus 2. So one answer we got, and you can also get the expression for xy by subtracting these two terms. So if you subtract it, you will get xy equal to 1 by 2y T2 plus 2 and T2 minus 2. Okay. So now let us move to the next spherical tensor, which is T2 plus or minus 1. So T2 plus or minus 1, the representation was, if you see it, is T2 plus or minus 1 is minus plus half ux vz plus vz ux, this term, and plus or minus I uy vz and vy uz. So let me take this term. So this was the term for T2 plus or minus 1. So now you have to put ux as x and v as x, uy as y, vy as y, and uz as z, and vz as z. So now let us see what we will get. Minus plus half. So you will get 2 times x z minus plus, plus or minus 2y yz. So that means you will get minus plus xz plus or minus I times yz, right? So if you take this minus plus here to these terms, then you will get minus plus xz, and this will become minus plus. So my minus with plus will become minus, plus with minus become minus. So it is minus only, right? So you have minus plus and there is plus minus. So minus plus will become minus and plus minus is minus. So this is the final expression. So here we have two terms, which is one is xz and other one is yz. So that means you can get the expression for xz and yz from here. So this means T2 one is minus xz minus iyz, and T2 minus 1 is xz minus I times yz. Now if you add these two terms, you will get the expression for yz. So I'm writing the final expression after rearranging the terms. So you will get minus 1 by 2y, and this is T2 1 plus T2 minus 1. So this is one terms. Now if you subtract these two terms, you will get the value for xz. You will get the expression for xz. So xz will be t2 minus 1 minus t2 1 divided by 2. Now let us move to the third component, which is t2 0. Okay. So that is the last term. So t2 0. So let us see what was the expression for t2 0. So the question was about xy, xz and x square minus y square. So we got for x square minus square here and xz is this one and xy is this. So the answer for the first part, we already got the answer. Okay. So there is no need to write down for the z. The third t20 for first part is done. So now let us see the second part. So the second part is the expectation value q is written as this expression. And here q is the quadruple moment. Now it is asking evaluate this matrix component where m prime is j minus 1, j minus 2 in terms of q and appropriate Clebsch-Gordon coefficient. Okay. So now let us see how we can calculate the B part. So for the B part, we are given Q as E alpha J m equal to J 3z square minus r square alpha J m equal to J. So this is given to us. So now if you see this term, so this is nothing but E alpha Z m equal to Z. You can write 3z square as 2z square minus z plus z square and r square is x square plus y square plus z square, and there is a minus term here, so you will get minus x square minus y square minus z square, and there is a term alpha z m equal to z. So this j square and this j square will cancel. So the term that will remain is E alpha z m equal to z 2z square minus x square minus y square alpha j m equal to j. So this is for the quadruple moment Q. So now if you see the third term was T20. So to find out this in terms of spherical tensor, what you can do, you have to use the T20 tensor component. So T20, let us see what we got in the previous question. So T20 was, so this is the T20 component, T20 expression, this one. And let us move to the next part. So T20 component is this one. So in this, we have to put ux as x. It will be 2z square minus ux vx will be x square minus uy vy will be y square. divided by root 6. So that means it is 2z square minus x square minus y square would be root 6 times t to 0. So now if you have to put this expression in the quadruple moment term. So that means the q will become e root 6 alpha j m equal to z t to 0 alpha j m equal to j, right? So this is the final term you got. Now we have to use the Wigner-Rickert theorem to solve this problem. So you can write this term as a product of a CG coefficient and a constant. Now let us write it in terms of this CG coefficient. So it will be JJ 20 JJ. There is a constant term which is independent of Q or M. This will be T2 alpha J. So I have written it in terms of JM, KQ and J1, M1. Okay. So now let us move to the part we have been asked about. So the question was to evaluate this term. So let us evaluate this term. So the term is E alpha j m prime x square minus y square alpha j m equal to j. So this one we have to calculate. So there is a term x square minus y square. So what we can do, we have to use this x square minus y square spherical tensor representation, which is this one. So that means this will be equal to E alpha j m prime and T2 plus 2 plus T2 minus 2 and alpha j m j m equal to j. So if you see this T2 plus 2 term, one minute. So if you see this, so there will be two terms, right? One is alpha j m prime T2 plus 2 alpha j m equal to j. The other one is 3 times alpha j m prime T2 minus 2 alpha j m equal to j. So now if you see the first term, you see this term. So for this, this one would be 0 because this here for this matrix component to be non-zero, what we should have? We should have m prime is j plus 2, which is not possible when j equal to j. So maximum value of m prime we get is j only. So for this term would be 0. So only non-zero component will be the second term. Okay. So we can have only this term, which is alpha j m prime T2 minus 2 alpha j m equal to j. So now you can write it in terms of this Wigner coefficient. This one. So if we write it, E, this will be J 2 minus 2 Jm prime, and there will be a term alpha J T2 alpha J. So that means you will get, if you put the expression for this one from here and this one. So you have the term here which is also present in this here. So you have to put it. So you will get JJ, sorry. So you will get JJ 2 minus 2 Jm prime, and here you will get Q divided by root 6 JJ 2 0 and JJ. Now this term would be non-zero when M prime is M1 plus Q, right? So M1 is this one, M1 is J and M2 Q is 2. So that means this term would be non-zero when M prime is same minus 2. So the answer will simplify into J 2 minus 2 J minus 2 Q divided by root 6 J 2 0 and J. So this is the final answer. So you have expressed the term that is given to us in terms of the quadrupole moment Q and the CG coefficient. So and again to see this term is 0 for this term is 0, what you can do. So I have only say ki M prime is J plus 2. That's why this is 0. So what you can do here is you have to express this term in terms of CG coefficient and this term. So if you express in terms of CG coefficient, what you will get? You will get this. The right side will be J and 2, and the left side will be J and M prime. So that means for the component for the coefficient to be non-zero, M prime should be J plus 2. So for that reason, it is 0. So okay, so let me write down. So if you write this term, so I am writing here. So you will get E J so you will get J and 1 is 2 M prime 2 there is a JJ here. So wait, this let me clearly write down. So the term is E alpha J prime T2 plus 2 alpha J n equal to J. So you can write in terms of CG coefficient. So if you write down, it will be J n prime. One is JJ 2 plus 2, and there is a term which is similar to this one. Let's say it is A. We will get a here. So now for this coefficient for to be non-zero, what we can have? M primes would be j plus 2, which is not for possible when j equal to j. So that means the first component is 0. So this is how you can solve the second problem. Now let us move to the third problem. Please go through the question once. So let me read out the question. So the question says, let OJS be a rank J tensor operator, and for J equal to half, you are given 3 by 2 minus 3 by 2 O J minus half 1 minus 1 is A. So this is given to you. So here J is half, that means it will be 3 by 2 minus 3 by 2 O half minus half 1 minus 1 would be A. Now the question is asking about this term. What will be the value for this component? So let us see. It is asking about 3 by 2 minus half O half half and 1 minus 1. So the way to solve is, you know that this will be proportional to CG coefficient, right? And this one is also proportional to CG coefficient. So you just have to divide it so that the constant term will cancel out. Okay. So we have to evaluate 3 by 2 minus half O half half 1 minus 1, and this is given to you, which is 3 by 2 minus 3 by 2 O half minus half 1 and minus 1. So this is given to us, which is A. So when we divide these two terms, the constant term will cancel out, and the terms that will remain is as the CG coefficient. So the CG coefficient for the numerator is, for this one, you can write it as 3 by 2 minus half and half 1 half half minus 1. So this is J1, J2, M1, M2. Now for the denominator part, what you have to do? You have to write down the CG coefficient, which is 3 by 2 minus 3 by 2, and this will be half 1 and minus half minus. So we have taken this as J1, J2, and this is M1, M2. Similarly, these two terms will be J1, J2, and this one M1, M2. So now if you see this term, so this is a stretched gate. So you know that 3 by 2 and minus 3 by 2 is equal to the uncoupled, the stretch gate in the uncoupled state, which is half 1 minus half, minus 2. So minus 3 by 2, there is also minus 1 minus half. So in 3 by 2, which is 1 half. So this is a stretched gate. So that means to take the inner product, it will be so half 1 minus half minus 1, 3 by 2 minus 3 by 2 would be 1. So this term would be 1. Now let us see what is the expression for the numerator, which is this one, 3 by 2 minus half, half 1, half minus 1. So if you are saying there is a minus half here, so the way we calculate the other terms of CG coefficient are, we take the stretch gate and we applied raising and lowering operator depending on the requirement. So from that or we can also apply the orthogonality condition to find out the other components of CG coefficient. So you are saying there is a minus half here. So minus half you can get it from minus 3 by 2 if you act a raising operator. So we have to apply a raising operator on this stretched gate 3 by 2 minus 3 by 2. And the right hand side will be J1 plus 1 plus J2 plus 1. Acting on this uncoupled state half 1 and minus half minus 1. Okay. Now let us see the individual terms. So I'm solving this step by step so that you will not have any doubts in any of this step. So J plus 3 by 2 would be H cut J into J plus 1, which is 3 by 2 into 3 by 2 plus 1 minus M into M plus 1. So M is minus 3 by 2, so it will be 3 by 2. M into M plus 1, so minus 3 by 2 plus 1. And this one would be 3 by 2. And this will become M plus 1. So it will become 3 by 2. And this one will become minus half. So just solve this and you will get h cut root 3 by 2 minus half. So this is for the left hand side of this equation. Now, if you want to calculate so you have to calculate the right hand side. So right hand side will be, this is J1 plus 1 plus J2 plus 1 acting on half 1 minus half minus 1. So J1 plus 1 will act on M1 and J2 will act on this one. So that means we will get two terms. So when J1 act on this minus half state, we will get H cut. So let me write down the J. This is J1, J2. This is M1 and 2. So it will be H cut, the first one, which is J1 acting on minus half state. So we will get H cut root over of J1 into J1 plus 1, which is half plus 1 minus M into M plus 1. So minus M will become plus M because there is minus half. So it will become half. And there is M plus 1, which is half plus 1. And this will become half 1 half minus 1. Right? So this is the first term. Now J2 plus will act on minus 1 state. So you will get H cut root over of J2 into J2 plus 1. So J2 is 1. 1 into 1 plus 1 minus M into M plus 1 M2 into M2 plus 1. So M2 is minus 1. So this will become 1 minus 1 plus M. This will become half 1 minus half and 0. So if you solve it, we will get h cut half 1 half minus 1 plus root 2 h cut half 1 minus half 0. But if you see the numerator, this one, we just have to calculate what is the inner product of 3 by 2 half minus half with half 1 half minus 1. So that means this one, half 1 half minus 1. So you have to take the inner product. So that means, let me write down explicitly what we get. So we get 3 by 2 minus half is, so this one is root 3 h cut is here. So it will go to the right hand side. So it will become 1 by root 3 half 1 half minus 1 plus root 2 by 3 half 1 minus half 0. Now you have to take the inner product with half 1 half minus 1. 3 by 2 minus half. So this will become 1 by root 3. Right? This term would be 0 when you take the inner product. So that means you will get 3 by 2 half minus half, half 1 half minus 1 is 1 by root 3. Right? So you got the expression for the numerator. So now you have to just put the value which is 1 by root 3 here. So this term is nothing but this term is 1 by root 3. So that means we wanted to calculate this term. So this term would be nothing but a by root 3. So the a will come here. So it will become a by root 3. So that means the answer is a by root 3. Okay. So the option that is correct is a by root 3. So this is based on the Wigner-Rickert theorem and the CG coefficient. So now let us solve some of the problems that is related to potential barrier and the Dirac delta function. So the fourth question is based on the potential barrier. So question is, consider a stream of particles of mass m, each moving in the positive x direction with kinetic energy E towards the potential barrier. So let us now first let us draw the potential barrier. The potential barrier is like this. It is 0 for x less than equal to 0 and it is 3 by 4 for x greater than 0. This is x and this is p of. Now we have a stream of particles which have energy E, which is greater than this potential barrier height. So we have a stream of particles which have energy E, and this stream of particles is approaching the potential barrier from the left hand side. So now they are asking about find the fraction of particle that will get reflected at x equal to 0. So to solve this kind of problem, what you can do, you have to divide. So you have different potential in different regions. So it's better to divide the regions in different parts. So let us call this x less than 0 as region 1. This one is region 2. So if you see region 1, which is x less than equal to 0. So here bx is 0, right? So that means if you write down the Schrodinger equation, it will be h cot square by 2 in dou square psi 1x by dou x square equal to e psi 1x. So that means dou square psi 1x would be, this would be equal to 2 in e by h cot square psi 1x. So if you now take this constant term is sum k1 square psi 1x. Now you got a second order differential equation. So this solution you already know. This is nothing but a oscillatory solution, which is a e to power I k1x plus b e to power minus I k1. So this is a wave or stream of particles that is incidenting on the potential barrier, and this is a stream of particle that get reflected at x equal to, that get reflected due to the potential barrier. So this is for the first reason. Now if for the second reason we have a non-zero value of potential. Let us see the reason 2. For x greater than 0, v of x is 3e by 4, right? So now if you put in the Schrodinger equation, this will become plus v of x psi 2 equal to e psi 2, right? So v of x is nothing but 3 by 4. Now if you rearrange it, so I'm writing down the final expression. So you will get, so just put v of x is 3e by 4 and take it to the right hand side. So you will get e by 4 psi 2x. So that means here we will also get a oscillatory solution. So you will get, so instead of taking, so this is psi 2, reason 2, what d square by dx square is minus 2me by 4h cot square psi 2x. You can write it down as minus k1 square divided by 4, because k1 is root of 2me by h cot square. You can write it as this. So now the solution will become, so take this k1 square by 4 is from k2 square. So that means k2 is k1 by 2, right? So you will get psi 2x is d e to power I k2x plus d e to power minus I k2x. But this term will not be present in reason 2, because in reason 2 there is no potential barrier beyond this barrier. So we have only barrier at x equal to 0. So that means we can have incident and reflected light in this reason 1, and in reason 2 we only have transmitted light. If let's say we have a case of two potential barriers. So that means here we will have incident reflected. Here also we will have incident reflected, and let us say this potential function is like this, and for this reason there will be only transmitted light. Okay, so that means for reason 2 we only have c e to power I k2x. Okay, now you can get the constant value A, B, and C by putting the boundary condition as well as the continuity condition. So if you apply the continuity condition in x equal to 0, so x equal to 0 is the boundary point. So you have to apply the continuity condition here. So continuity condition is psi of x at x is 0 must be equal to psi 2x at x equal to 0. So psi 1x is nothing but this one, a e to power ikx plus b e to power minus ikx. So if you put 0 here, so you will get a plus b. And psi 2 is c e to power ik2x. So it will become a plus b equal to c. Now the derivative, first order derivative will also be continuous at x equal to 0. And during this derivative continuity, remember that first we have to take the derivative, then put x equal to 0. It's not like you have first put x equal to 0 and then take the derivative. It's not the proper way. So the proper way is first take the derivative and put x equal to 0. So if you take the derivative, you will get ik1 a to power minus ik1x. Let me see, a plus b. Okay. So this will be plus and minus ik1 b e to power minus ik1x at x equal to 0, and this one is ik2 c e to power ik2 x at x equal to 0. So now you can put the value for x, which is 0. So you will get ik1 a minus b equal to ik2 c. So k2, you know, k2 is nothing but k1 by 2, right? So you get it from here. K2 is k1 by 2. So if you put it, you will get a minus b equal to c by 2. Okay, so we get one a plus b equal to c, and another one is a minus b equal to c by 2. So to find out what is the fraction of particles that get reflected, so this depends on the coefficient for the reflected light b and the coefficient for incident light squared. So, this is this coefficient and this coefficient b by a squared. So that means we have to calculate what is the expression for b by a. So b by a will get it from here also. So this will be 1 minus b by a. This will be c by 2a. So now if you multiply 2 years, so we will get 2b by a is c by a. The second one will give 1 plus b by a equal to c by a. So that means 2 minus 2b by a is 1 plus b by a, right? So from here you can get b by a is 1 by 3. That means b by a square is 1 by 9. So that means the 1/9 of this particle will get reflected when we have a potential barrier like this. So this is how you can calculate what is the fraction of particle that will get reflected. Okay, so now let us move to the next question. So the next question is also a potential barrier problem. So let me read out the question. The question is, consider a one-dimensional problem of particle of mass m in a potential barrier V infinity for x less than 0. So for x less than 0, we have V is infinity and V is 0 for x when x is between 0 to a, and V is V0 for x greater than a. So for x greater than a, it is V0. Now obtain the wave function and so that the bound state energy, which is E less than V0, are given by this transcendental equation. So first we have to calculate the wave function. So the way to solve it, like I said before, we have to solve the Schrodinger equation in different regions. So we have region 1 where V is 0 and region 2 where V is V0. Okay, so let us solve region 1. So for region 1, it is 0 is less than and V is 0. So that means here, and we are solving it for bound state. So for bound state, E is less than V0. Okay, so remember it. So now if you want to solve in reason 1, the Schrodinger equation, it will be h square by 2m dou square psi 1 by dou x square equal to E psi 1. So that means dou square psi 1 by dou x square would be minus 2m E by h square psi 1. So let's take this constant term is minus k1 square psi 1, where k1 square is 2m E by h square. And the solution, you already know, this will be oscillatory solution. So this will be, you can write it as in terms of exponential term as e to power ikx plus b e to power minus ik1x. You can also write it as a sine k1x plus b cos k1x. So both are valid. Okay. So for convenience, I have taken this one so that I can get the transcendental equation. So this is 1. For reason 2, we have which is x greater than a and v is v0. So for reason 2, the Schrodinger equation is h square to 2m d square psi 2 by dou x square plus v0 psi 2x equal to e psi 2x. And e is less than v0. So that means dou square psi 2 by dou x square would be minus 2m e minus v0 by h square psi 2. So as e is less than v0, it is better to write v first, then e, and take this constant term as k2 square. K2 square psi 2x. So the solution for this one would be psi 2x would be, it's not oscillatory, it will be c e to power minus k2x plus d e to power k2x. Right, this is the general expression. So now what you have to do, you have to put the boundary condition as well as the continuity condition, right? So the continuity condition is the wave function should be continuous at the boundary, which is x equal to a, and the derivative dou psi by dou x would be continuous at x equal to a. Okay. So before solving that, let us see what is the boundary condition. Boundary condition is Vx is infinity for x equal to 0. That means this psi1x should be 0 when x equal to 0. So psi1x is a sine k1x plus b cos k1x, right? It should be 0. This term would be always 0 and this is 1. So that means b is 0 for our case. So that means this psi1x is a sine k1x. And there is another, this is for reason 1, and for reason 2, for particle, given it the particle is confined, that means the exponentially growing factor in reason 2 should be 0, right? So what I mean to say is when x tends to infinity, psi 2x should goes to 0. So let us see what is psi 2. Psi 2 is c e to power minus k2x plus d e to power k2x. So when x tends to infinity, this will be the exponentially growing factor. So that means this term would be 0. So that the particle, we can have a physically acceptable solution. So psi 2x is c to power k2x. So now we have the final expression for the wave function, which is psi of x. Reason 1 is psi 1x, which is a sine k1x. Reason 2 is psi 2x equal to c to the power minus k2x. This is for reason 1. This is for reason 2. Now we have to apply the boundary condition to get the value of a and c and to get the transcendental equation. So the first continuity condition is wave function is continuous. Okay, so psi 1x equal to psi 2x when x equal to a. So let us see, is psi k1 at x equal to a, it will be a, and psi 2 is c to the power minus k2 a. Right? And now the second continuity condition is the derivative. The derivative would be continuous also. Equal to dou psi 2x dou x at x equal to a. So dou psi 1 dou x will be a k1 cos k1x, and this one would be minus k2 c to the power k2 x at x equal to a. So that means we get a k1 cos k1a equal to minus k2 c e to the power minus k2 a. So we have two equations. This is 1 and this is 2. So to get the transcendental equation, what we can do, we have to divide 1 by 1 and 2. So if you divide 1 by 2, we will get 10 Ka equal to minus K1 by K2. So you have to just put the expression for K1 and K2. K1 is nothing but root over of 2m E by h cot A, and K2 is, so here you have to put 2m E by h cot square, and K2 is 2m V0 minus E h cot squared. So this will be minus root over of E minus V0 by E. So this is the transcendental equation which was asked in the question. Okay. So we already got the transcendental equation, which is this one. So now let us move to the next question. The sixth question is, if a particle is subjected to the potential V of x equal to kx squared plus bx to the power 4, where b is a positive, then energy eigenfunction are parity eigenfunction. So it is telling that the parity eigenfunction are equivalent to the energy eigenfunction. So that means if these two operators, for energy it is Hamiltonian and for parity it is P. So for both P and E, if they have common eigenfunction, that means the commutation relation of HP should be 0. So that means HP minus PH acting on psi x should be 0. So V of x is this. If I write down V of minus x, should be kx square and bx square 4. So that means V of x is minus x is V of x. So potential is an even function. Now if you take, let's say, the first term HP psi of x. So HP is H is minus h cot square by 2m dou square by dou x square plus P, not plus V. There is a P term here acting on psi of x. So this will be psi of minus x, right? When P acts on psi of x, it will become psi of minus x. So that means we have minus h cot square by 2m dou square by dou x square psi of minus x plus v of x psi of minus x. This is for first term. For pH, so for pH, first the Hamiltonian will act, then the parity operator. So you will get h cot square by 2m dou square by dou x square psi of x plus v of x psi of x. Now when p operator will act, it will become h cot square by 2m dou square by dou x square will become dou square by dou x square, and psi of x will become psi of minus x, and this will be v of minus x and psi of minus x. But we know that v of minus x is v of x, right? We have proved it. So if you compare these two terms, okay, term 1 and 2, together this HP and PS, they both are equal when they act on a arbitrary state, which is psi of x. So that means this commutation relation of HP would be 0. So they will have a common eigenstate. So if H is eigenstate, the eigenstate of Hamiltonian is energy eigenfunction. So that means the parity operator will have energy eigenfunction. Okay. Now let us move to the next question. Question 7. So question 7 is based on Dirac delta potential. So we are given consider a particular mass m in one dimension bound by delta function. Delta function which is v of x is minus a delta x, where a is a real positive. Now they are asking about the bound state energy of the system would be. So we have to calculate the bound state energy of the system. Let us see what is the plot for the potential. So we have v of x is minus a delta x. So that means at x equal to 0, we have a Dirac delta potential. So there are two reasons, reason 1 and reason 2. So let us solve reason 1. So for reason 1, x is less than 0, right? So that means, and the potential is 0. So that means h cot square by 2m dou square psi 1 by dou x square equal to E psi 1. So that means dou square psi 1 by dou x square would be minus 2m E by h cot square psi 1. And remember, we are calculating it for bound state. For bound state, E is less than 0. So that means this is a positive term, not a negative term. So this solution will you will get. So if you take this one as k1 square psi 1, the solution we will get is psi 1x would be a e to power k1x plus b e to power minus k1x. But there is a catch here. We know that for reason 1, for bound state, if for reason 1 x is less than 0. So if we have a bound state, that means psi 1x should goes to 0 when x tends to minus infinity. So that means the exponentially growing factor should be 0 for reason 1. So the exponentially growing factor, if you see 1 and 2, when x tends to minus infinity, this term will be, this b e to power minus k1 will grow exponentially. So that means psi 1x should be a e to power k1x for x less than 0. Okay, for reason now let us solve in reason 2 for x greater than 0. For reason 2, what we have? We have h cot square by 2m dou square psi 2 by dou x square equal to e psi 2x. So we have same kind of expression. So you can take it as k1 square psi 2. And the solution would be same. Instead of AB, we'll have a C coefficient. This is k1x plus d e to power minus k1x. But similar to the condition for reason 1, here we also have, if we for reason 2 x is greater than 0, so that means for bound state, this psi 2x should goes to 0 when x tends to infinity. So we have to neglect the exponentially growing factor. If you see c e to power kx, it is a exponentially growing factor if x tends to infinity. So that means this should be 0. So psi 2x should be d e to power minus k1x. So now we got the wave function in different reason, right? So for reason 1, we get psi 1x. For reason 2, we get psi 2x. Psi 2x is nothing but d to power k1x. This is a to power k1x. For x less than 0 and for x greater than 0. So we got the wave function. Now let us see what the question was asking. Now it was asking about the bound state energy of the system. So now we have to use the continuity condition. So continuity means the wave function should be continuous. Psi 1x should be psi 2x at the boundary which is x is 0. So that means a equal to d. Okay. But the first derivative is not continuous because there is a Dirac-Delta function. So this psi 2 by dx x equal to 0 minus d1 by dx x equal to 0 should be equal to minus 2ma by h cot square psi x equal to 0. So this is the discontinuity condition of first order derivative when we have Dirac-Delta function. So in the answer sheet, I have derived how you got this expression. So please go through the steps. It's explicitly written. So basically, we got this kind of expression by solving the Schrodinger equation. So please go through the derivative one so that you can understand the steps. Okay. So now you have to put the expression for psi 2. Psi 2 and d psi 2 by dx would be minus k1d e to power minus k1x minus d psi 1 by dx would be k1a e to power k1x, and this is x equal to 0, and this is 2ma by h cot square psi at x equal to 0, which is nothing but d or a. So now you have to just put 0. So this is k1a minus 2ma by h cot square d, right? And a is d, so that means we will get k1 is ma by h cot square. So if we solve it, we put the value of k1, which is root over 2ma by h cot square minus 2ma by h cot square equal to ma by h cot square. So from this, you will get the energy for the bound state, which is nothing but minus ma by 2h cot square. So this is the bound state energy in the presence of a Dirac potential at x equal to 0. So the answer will be D. So let us move to the next question. So the next question is, it's a simple, you can directly calculate it. So it is given covariance state alpha is an eigenstate of ladder operator A with eigenvalue alpha. So that means A alpha is alpha times alpha. Now they are asking about the expectation value of the A dagger. Okay. So alpha A dagger alpha. This is how much? This is what? So what you can do, you just add A dagger A and subtract A dagger A. This is the commutation relation of A dagger, which is nothing but 1. So you will get 1 here plus alpha A dagger A alpha. So A alpha will give alpha times alpha. Now this, so you can also write it as alpha A dagger is alpha star alpha. So that means this is alpha star alpha, right? So you will get 1 plus alpha square. Okay. So this is the expectation value for A dagger. So answer will be answer C. So this was the simplest question. Now let us move to the next one. The next one is also a Dirac delta potential. So what is given? It is given a particle of mass m move non-relativistically in one dimension in a potential given by v of x equal to minus a delta x. Okay, it is given where delta x is the usual Dirac delta potential. The particle is bound, that means E is less than 0, and find the value of x0 such that the probability of finding the particle in this region where mod x is less than 0 is exactly half. So the potential is similar to the one we have solved before, like I think the 7th question. So instead of I think lambda, we have a here. And there is a reason 1 and reason 2. And the particle is also bound. So this is similar to this problem. Okay. So, okay, the V is also same. So that means the wave function would be this form. Okay. So I am directly writing down the expression for the wave function. So psi of x would be a e to power kx or x less than 0 and a e to power minus kx or x greater than 0, where k is root over minus 2m divided by h code square, right? And the discontinuity is the discontinuity condition will give non-zero will give a non-zero value of derivative in both the left and right hand side. So from the discontinuity condition, like the one we have solved here, I think. This continuity condition will give K as MA by H cot square. So we will have K as MA by H cot square. Now we have to calculate the probability. So probability, we have to take the square of this wave function. So probability for finding the particle at x less than x0 is given is half. Okay. So that means you can separate out x0 to 0 psi 1 x square dx plus 0 to x0 psi 2 square dx equal to half. Now if you put the value of psi 1 and psi 2, you will get this one is a square minus x0 to 0 e to power 2kx dx plus a square 0 to x0 e to power minus 2kx dx equal to half. Now if you solve this integration, so this integration is simple, it is not difficult to calculate it. So if you calculate it, you will get a square by k equal to a square by k 1 minus e to power 2kx0 is half. So a square k we can get it from the normalization condition. So the probability is the particle is bound. So that means the probability of finding the particle from minus infinity to x to infinity is 1. So this is 2 times a square 0 to infinity e to 2kx. So I have skipped some of this step. You just have to put the value of psi 1 and psi 2, psi 1 square, psi 2 square. So from that you can get this expression. So this is easy. That's why I'm skipping these steps. So from this, if you calculate it, you will get a square by k is 1. So now you have to put a square by k is 1 here. So that means we will get 1 minus e to power minus 2kx0 is half. So that means e to power minus 2kx0 is half. So if you take the ln in both sides, you will get 2kx0 is ln half. And from this, we will get x0 is 1 by 2k ln 2. And 1 by k value is ma by h cot square ln 2. So this is the final expression. So for the probability in this region to be half, we have to have x0 equal to h cot square by 2ma ln 2. So this one ln half, you can write it as ln 1 minus ln 2. This is 0. And now I have just rearranged. I have taken minus 2k to the right hand side and got this expression. So this is the answer to this question. Okay. Now let us see the next problem. This is also based on the Dirac delta potential, but it's different. So it is given a particular mass moving in one dimension is confined to the region 0xL by infinite squirrel potential. In addition, the particle experiences a delta function of strength lambda located at the center of the well. So there is a delta potential here. And the Schrodinger equation which describes the system is within the wall is this. Now find the transcendental equation for the energy eigenvalue E in terms of mass, potential strength, and size L. So for this, it is also similar to the question number 7. So you just have to find out the wave function in different region and apply the continuity condition as well as the boundary condition to get the transcendental equation. So given v of x, so this I will solve it quickly because it is already explained in the previous part. So v of x is this. Now we have two reasons, reason 1 and reason 2. So in reason 1, for 0x L by 2, we have psi 1x. So if you we have psi 1x, and for reason 2, which is L by 2, x and L. we have psi2x. So psi1 and psi2 expression we can take from the infinite 1D potential. So for infinite 1D potential, we know that psi1 psi of x is a sine k. So we can also express psi1 and psi2 in terms of the sine function. So let us see. So we can express psi1x as a sine k1 k1x and psi2 is a sine. So this is a1, this is a2, a sine. So v is 0 in both the reason, right? So that means k1 is equal to k2. So I can take it as k. So this is also kx, not kx, this is k x minus L by 2. Wait, let me clearly write it down. So this will be a1 sine kx and this is a2 sine k x minus L. So this is this I have taken a psi1 is a1 psi1x so that we know that for x equal to 0 it should be 0. So if you put x equal to 0, psi1 vanishes. Now we also have x, for x equal to L, this psi1 should be 0, right? Because it's an infinity potential. So here also the potential, the wave function should vanish. So that's why I have taken kx minus L so that when x equal to L, this term vanishes. So that means we have wave function psi of x is psi1x, psi2x, which is a1 sin kx for 0 x L by 2, and this is a2 sin k x minus L for L by 2 x and L. So we got the wave function. Now what you have to do? We have to apply the continuity condition of wave function as well as the discontinuity of derivative to find out the transcendental equation. Okay. So psi1x. So please go through the notes also because in notes I have derived how you got the discontinuity condition. So that if you know how the discontinuity is derived, then you can easily apply it to other kind of potential, other kind of Dirac delta potential. Okay, so let us see the first continuity. The first continuity is psi of x is continuous. So that means psi1x equal to psi2x at x equal to L by 2. So the boundary point is x equal to L by 2 where we have a Dirac delta potential. So that means this will be a1 sine kl by 2 and this is a2 sine minus kl by 2. So this equation gives a1 is minus of a2. So this is the first continuity. The other one we have the discontinuity condition. Okay. So the discontinuity condition is so the discontinuity is dou psi1 by dou x minus dou psi2 psi2 psi1 by dou x at x equal to L by 2 is equal to lambda times psi L by 2 minus lambda times psi L by 2. So this is the discontinuity condition. So now what you have to do? You have to put the value of psi2 and psi1. So psi2 is dou by dou x. This is a2 sine k x minus L minus dou by dou x A1 sine kx at x equal to L by 2 equal to minus lambda psi at L by 2 is nothing but A1 sine KL by 2. Now you have to just take the derivative and put x equal to L by 2. So that means this first term will give A2 K cos K cos K x minus L minus A1 K cos Kx, and this we have to evaluate it in x equal to L by 2, and the right hand side is lambda A1 sine KL by 2. So now we have to put x equal to L by 2 here. So we will get A2 K cos KL by 2 minus A1 K cos KL by 2 equal to minus lambda A1 sine KL by 2. So I have made a mistake here. So 2 will be, this is K by 2. Now put A2 equal to minus A1. If you put it and solve it, you will get 10 KL by 2 equal to minus K h squared by m lambda. So this is the transcendental equation. So you have to just rearrange this term. Now in terms of energy, you can write it as root over of 2 me by 2 h squared L equal to minus root over of 2m by E h squared by lambda. So this is the answer. Okay. So now let us move to the next problem. So next problem is also related to the previous problem, question number 10. So instead of the transcendental equation, in this question they are asking about the change in what will be the effect of a Dirac potential in wave function as well as the energy. Okay, so let me read out the question. So it is given an infinitely deep 1D potential squarable confines a particle to the energy x0 when x lies between 0 to 1. Now it is telling scales the wave function for its lowest energy state. So for the lowest energy state, we have wave function like this, right? So we have a sine curve and the maxima is root over of 2 by L. So the ground state wave function is psi 0x, which is root over of 2 by L sine pi x by L, and the energy is E0, which is h square pi square by 2m. Now, what is the next part? Next part is if a repulsive delta potential V of x is V of x equal to lambda delta x L by 2. So there is a repulsive potential at x equal to L by 2 is added at the center of the wall. Now scale the new wave function and state whether the energy increases or decreases. So the question is asking about after adding a delta potential here. So we have a delta potential here, which is repulsive type, x equal to L by 2. So now if you have a delta potential here, so how this energy as well as the wave function get affected? So in the previous question, question number 10, we saw the wave function formalism like the wave function is reason 1 and 2 is nothing but a1 sine kx or 0 xl by 2, and for reason 2 it is minus a1 sine k x minus L or L by 2 x and L. So these are the wave function in different region. Now let us see the question. So the question is asking about the new ground state wave function and what about the energy. Okay. So this and the continuity condition is condition for this region 1 and 2 are psi1x equal to psi2x at x equal to L by 2 and the psi1x psi2x minus 2 psi into x equal to 2m lambda by h square psi1 L by 2. This is evaluated at x equal to L by 2 and the transcendental equation we got is 10 k L by 2 is kh square by m lambda. So that means the ground state wave function, let's say psi 0 prime for this case where we have a delta potential. So this will satisfy all this equation, right? So that means this psi 0, and if you take for ground state k is k0 prime. If you take it, then it is from this equation, it is showing that this k0 prime should satisfy tan k0 prime L by 2 equal to, and there is a minus term here, right? The previous problem, if you see question number 10, there is a minus here, so it will be minus k square I m lambda. So that means this is k0 prime. So this equation tells this k0 prime is negative. Wait, not k0 prime. This is telling k0 can never be negative, so it will be 10. So it is telling 10 is negative, right? So there is a minus here, so it is telling 10 is tan function is negative. So if you see the tan x curve, so if you see for region between pi by 2 to pi, we have a negative tan curve. Okay, this is the lowest region for which we get a negative tan. So for this reason, this tan curve is negative. So for 0 to pi by 2, it is positive. It is like this. So we can't take 0 to pi by 2. So the next reason is pi by 2 to pi. So that means this k0 prime L by 2 should lie between pi by 2 to pi so that this equation is satisfied. So that means this k0 is lying between k0 prime is between 2 pi a by L to pi by L. So this pi by L, if you see for the infinity potential without no barrier, no potential, Dirac potential. For this, the ground state k0 is pi by L. So that means this k0 prime in the new means when we have a Dirac potential here. For this it is k0, for this it is k0 prime. So this k0 prime is greater than k0. That means the energy which is h square k0 prime square by 2m for the ground state is greater than h square k0 square by 2. So now this is telling that if we add a repulsive potential in the center, then the energy of the ground state increases. Okay, so the effect on the energy is that the energy will increase. Now coming to the wave function. So wave function you already know for infinity. So this is kind of this. Now we have a discontinuity in x equal to L by 2 because of the repulsive potential. So that means now the wave function will become like this, so that the first order derivative is discontinuous in this region 1 and region 2. So this is the new ground state wave function. So this is the new ground state wave function that you will get. Now there is another part. Now it is telling if the ground state energy was E0, then what does it become when lambda tends to infinity? So instead of a constant value of a finite value of lambda, we have lambda tends to infinity. So that means we have a infinity barrier in the middle, right? So the middle will become a infinity potential barrier. So that means now this L becomes E by 2 because there is a 1D potential here and 1D potential here also. So E0 was h cot square I square by 2ml square. Now we'll have E0 prime, which is square h cot square by 2m pi square L by 2 square. So this will become 4 times E0. So this ground state energy will become 4 times when the lambda tends to infinity. Okay. Now let us solve the final problem, and after that we will end this section. So the final problem is based on spherical harmonics. So it is asking about the expression for 210 Ez, where the operator is Ez equal to E cos theta. So it is asking about 20 Ez 10. What will be this when Ez is mod E cos theta? So this is simple. You just have to use the expression for spherical harmonics for 20, which is root over 5 by 16 pi 3 cos squared theta minus 1, and for 10 it is root over 3 by 4 pi cos theta, and given Ez equal to mod E cos theta. So to find the expectation value, you just have to put the expression for y20, y10 in the integral. So I put y10 first. So this will be y star 20 is 8 cos theta sin theta d theta d phi. So this cos theta is for y10. Now what you have to do, you have to put the expression for y20. This is 5 by 16 pi integration 3 cos squared theta minus 1 cos squared theta sin theta d theta d phi. Okay, so d phi integration is from 0 to 2 pi, right? It will give 2 pi. So we will get, so this is 15. Okay, There is a EZ here also. So EZ. So this there will be mod here. This will be 8 pi. There is a 2 pi mod integration cos square theta 3 cos square theta minus 1 sin theta d theta from 0 to pi. So for to solve this, what you can do, you just have to make substitution. Let's take cos theta equal to t. So that means sin theta d theta will be minus dt, and when theta tends to 0, t will tends to 1, and theta tends to pi, t will tends to minus 1. So you have to make the substitution. If you make it, you will get integration t square 3t square minus 1 dt from minus 1 to 1. So if you solve this integration is easy. So if you solve it, you will get, I am writing the final answer. This is 2e by root over 15. So this will be the answer. Answer D. So now we have already we have solved the problems of the section. Let us end the meeting now. So we'll meet on next Saturday, which will be a summary section. So please try to attend that section. So for now, bye.